frames that snapped at speed, brakes that melted on mountain passes, engines that seized without warning and threw riders into oncoming traffic. This is the story of 14 motorcycles where the engineers went too far, and why too far turned out to be exactly far enough. Number 14. Suzuki RE5, 1975. In 1974, Suzuki looked at what every other motorcycle manufacturer was doing with conventional piston engines and decided that pistons were the wrong answer entirely. The RE5 used a Wankel rotary engine, the same concept Mazda was using in their RX car. Instead of pistons moving up and down, a triangular rotor spins inside an oval-shaped housing. No valves, no camshaft, no timing chain, just a rotor, a housing, and physics. Think of it this way. A conventional engine is like a person running, legs going up and down, constant impact, constant reversal of direction. A rotary engine is like a person on a bicycle, smooth circular motion, no impact, no reversal. That is why rotary engines are so incredibly smooth. The rotor never stops, it never changes direction, it just spins. Suzuki co-developed their rotary with NSU in Germany, who held the Wankel patents. They built the engine to aircraft tolerances, machining precision far beyond what any motorcycle engine required. The apex seals, which are the critical wear component in any rotary, were manufactured to specifications tighter than anything in Suzuki's existing motorcycle lineup. The result was a motorcycle that vibrated less than a sewing machine, produced smooth and linear power, and confused absolutely everybody who rode it. Reviewers did not know what to compare it to. The riding experience was unlike any motorcycle that had existed before. It was also a commercial disaster. Riders were suspicious of the unfamiliar technology. Mechanics had no training on rotary engines. Fuel consumption was roughly 50% higher than comparable piston bikes. Suzuki lost money on every single unit and discontinued the RE5 after just 2 years. But here is the overbuilt detail. Surviving RE5 engines, properly maintained, are still running 50 years later. The engineering was not the problem. The timing was. Suzuki built a motorcycle for a future that never arrived. Number 13 also brought a technology to motorcycles that nobody had asked for. But while Suzuki borrowed from the car world, Honda borrowed from something even more unlikely, Formula One turbocharging, and bolted it onto a commuter bike. Number 13. Honda CX500 Turbo, 1982. The Honda CX500 was a perfectly competent, perfectly boring, bulletproof V-twin commuter that European courier companies rode past 200,000 miles. It did not need turbocharging. Nobody was asking for a turbocharged version. Honda built one anyway. The CX500 Turbo was the world's first turbocharged production motorcycle. Honda fitted an IHI turbocharger to the 497cc V-twin, added fuel injection, which was itself extremely rare on motorcycles in 1982, and created a machine producing 82 horsepower from an engine that normally made 50. The level of engineering was absurd for a motorcycle at this price point. The fuel injection system used a computer in 1982, when most cars still had carburetors. The turbo system had its own oil supply with dedicated cooling lines. Honda engineered a programmed fuel injection system that adjusted mixture automatically based on boost pressure and throttle position. This technology would not become standard on motorcycles for another 20 years. It was also the first motorcycle with a fully digital instrument cluster. Everything electronic. In 1982, Honda spent more money developing the CX500 Turbo than they had spent on some entire model lines. Sales were modest. The Turbo added significant cost and complexity to a platform that had been beloved specifically for its simplicity. Honda was effectively selling a space shuttle to people who had been perfectly happy with a bicycle. But the engineering legacy was undeniable. The fuel injection and electronic engine management systems pioneered on the CX Turbo became the foundation for Honda's entire electronic fuel injection program. Honda overbuilt with technology the market was not ready for. Number 12. Overbuilt with a concept so radical that 30 years later, most riders still do not understand what it does or why it matters. Number 12. Yamaha GTS 1000, 1993. Every motorcycle you have ever ridden uses telescopic forks. Two tubes sliding inside each other, connected to the front wheel at the bottom and the frame at the top. Simple, proven, and used on essentially every production motorcycle since the 1940s. Yamaha looked at telescopic forks and decided they were fundamentally wrong. The GTS 1000 used a rad hub center steering system designed by James Parker. Instead of forks, the front wheel was held in a single-sided swing arm, connected to the frame through a complex linkage. The steering input came through a separate mechanism entirely. Why does this matter? Because telescopic forks have a fundamental engineering compromise that most riders never think about. When you brake hard on a conventional motorcycle, the forks compress, the front end dives. The geometry of the motorcycle changes mid-corner or mid-stop. The trail changes, the wheelbase shortens. You are riding a machine whose fundamental handling characteristics change every time you use the brakes. Hub center steering eliminates this entirely. Braking forces are separated from steering forces. The geometry stays constant, regardless of what the brakes are doing. The motorcycle handles exactly the same under maximum braking as it does under no braking at all. In engineering terms, it is objectively superior. Yamaha built the GTS 1000 with the confidence that riders would understand why this mattered. They were wrong. Most riders found the front end feeling strange and unfamiliar. Magazines praised the engineering and questioned the market appeal. Yamaha discontinued it after 2 years. The technology has since appeared in MotoGP prototypes, in Bimota's Tessie series, and in academic research on motorcycle dynamics. Yamaha was right about the engineering. They were 20 years early on the audience. Yamaha overbuilt the suspension. Number 11 overbuilt the entire engine concept by putting a type of motor into a motorcycle that the motorcycle industry had universally agreed was impossible. Number 11. Norton Rotary, 1987. After Suzuki's RE5 failed commercially, the motorcycle industry reached a consensus. Rotary engines do not belong in motorcycles. Too thirsty, too unfamiliar, too complex for the average mechanic. Norton apparently did not attend that meeting. In the mid-1980s, the Norton engineering team, working with a budget that would embarrass most garage startups, developed a twin-rotor Wankel engine specifically designed for motorcycle use. Not adapted from a car, not licensed from another manufacturer, built from scratch for a motorcycle. The engine was air-cooled, compact, and produced around 85 horsepower in road trim. In racing specification, the Norton Rotary produced well over 130 horsepower and won the Senior TT at the Isle of Man in 1992, beating every Japanese and Italian four-stroke in the field, a rotary engine. At the TT, in the senior class, winning against motorcycles with 20 times the development budget. The police version, the Norton Commander, was adopted by several British police forces and built a reputation for smooth, reliable highway patrol duty. Officers who rode them consistently rated the engine's smoothness as superior to any piston motorcycle they had used. Norton was right about rotary engines in motorcycles. They were also chronically underfunded, mismanaged, and eventually destroyed by corporate decisions that had nothing to do with engineering. The rotary motorcycle that won the TT was abandoned not because it failed, but because the company around it collapsed. Have you ever ridden or seen a Norton Rotary in person, or any rotary motorcycle? These are some of the rarest overbuilt machines in existence. If you have a story, drop it below. Norton put an impossible engine in a motorcycle and won the TT with it. Number 10 did something equally strange. They took a car engine, turned it sideways, and told the world it was a motorcycle. Number 10. BMW K100, 1983. There is a test that motorcycle mechanics sometimes use to explain the BMW K100 to people who have never seen one. They say, imagine taking a 4-cylinder engine out of a small car, rotating it 90 degrees so the cylinders point forward instead of up, and then building a motorcycle around it. That is not a simplification. That is literally what BMW did. The K100 earned the nickname the Flying Brick because the engine looked like one and was roughly as indestructible. An inline-4 with the crankshaft running lengthwise instead of across the frame. Fuel injection standard, shaft drive. A Bosch engine management system more commonly found in German sedans. BMW did not borrow car technology for the K100. They used actual car engineering processes. The engine block was cast using techniques developed for BMW's automotive division. Tolerances were held to automotive standards, which in 1983 were significantly tighter than motorcycle standards. The result was an engine that mechanics describe with a word they rarely use for motorcycles: agricultural. Not as an insult, as the highest possible compliment. The K100 engine has the refinement of a tractor and the longevity to match. Owners have documented K100 engines running past 300,000 miles on original internals, not rebuilt. Original. The engine was simply overbuilt to a standard that normal motorcycle use could never stress. If you rode a K100 every day for 20 years, the engine would still be in the early stages of its design lifespan. Even the shaft drive was over-engineered. BMW used a universal joint system designed to last the lifetime of the motorcycle, which in K100 terms means essentially forever. The only regular maintenance most K100 owners report is oil changes and brake pads. Everything else simply refuses to wear out. BMW overbuilt for the road. Number 9 was overbuilt for something far harsher than any road. It was overbuilt for actual combat. Number 9. Kawasaki KLR 650, 1987. In the mid-1980s, the United States Marine Corps needed a motorcycle that could run on diesel fuel, survive desert conditions, carry military equipment, and be maintained by soldiers with basic mechanical training in field conditions. Kawasaki's answer was a militarized version of the KLR 650, designated the M1030 M1. The civilian KLR 650 was already overbuilt by normal motorcycle standards. A 651cc single-cylinder engine, tuned for torque instead of horsepower, producing about 40 horsepower, roughly half of what the engine was theoretically capable of. Kawasaki deliberately left enormous engineering margin in the engine. It operates so far below its mechanical limits that the internals barely stress under normal use. That is why these engines routinely survive 100,000 miles with nothing more than oil changes. But the military version took overbuilt to another level. The fuel system was modified to accept JP-8 military jet fuel as well as diesel and standard petrol. The electrical system was hardened against electromagnetic interference. The frame was reinforced for carrying equipment loads that no civilian rider would ever mount. The civilian version inherited all of that structural conservatism. If you buy a KLR 650 and ride it to work every day, you are riding a motorcycle that was engineered to survive combat conditions. Your daily commute is a holiday for this machine. It was designed for environments where breakdown meant being stranded in territory where nobody was coming to help. Adventure riders figured this out decades ago. The KLR 650 became the default choice for riders crossing remote continents, Africa, South America, Central Asia, because it could be repaired with basic tools. Parts were available globally, and the engine refused to die regardless of fuel quality, temperature extremes, or rider neglect. The KLR was built for the military. Number 8 was built for an equally demanding customer, European police forces, and police requirements are, in some ways, even harsher than combat. Number 8. Honda ST1100 Pan-European 1990. Police motorcycles have a specification sheet that would terrify any normal motorcycle manufacturer. The machine must run for 8 to 12 hours per day in stop-and-go traffic. It must idle for extended periods in hot weather without overheating. It must accelerate from standstill to pursuit speed repeatedly. It must carry an additional 60 to 80 kilograms of equipment beyond the rider's weight. And it must do all of this for 100,000 miles before a scheduled replacement. Honda built the ST1100 to meet that specification and then added margin. The engine is a 1084cc longitudinal V4, the same configuration Honda used in its racing program. Shaft drive eliminates chain maintenance entirely. The cooling system was designed for sustained low-speed operation in full summer heat with a fully loaded machine. Honda tested the ST1100 in conditions that simulated the absolute worst-case scenario a police rider could encounter and then added safety factors on top of the results. European police forces, particularly in Britain, France, Germany, and the Netherlands, adopted the ST1100 as their standard motorcycle and rode them into territory that no civilian would consider acceptable use. 10-hour shifts in traffic, rain, cold, heat, repeated hard stops from highway speed. Equipment loads that turned the motorcycle into a mobile office. Civilian owners discovered that a motorcycle built to survive police abuse could survive anything they would ever do to it. ST1100 forums are filled with odometers showing 200,000 miles, 250,000 miles, some approaching 300,000, often on original engines with nothing more than scheduled servicing. Honda did not market the ST1100 as overbuilt. They marketed it as a sport tourer. The overbuilt part was hidden underneath, visible only after a decade of use, when the motorcycle simply refused to show its age. Honda overbuilt for police. Number 7, overbuilt for a completely different reason. Because the founder of the company wanted to build something that no other motorcycle manufacturer would consider even attempting. Number 7. Honda Goldwing GL 1000 1975. In 1974, every manufacturer in the motorcycle industry agreed on one thing. Motorcycles were powered by inline engines, usually twins or fours, with the cylinders pointing upward. That was the formula. Nobody questioned it. Honda questioned it. The Goldwing GL 1000 used a water-cooled flat-4 engine, 4 cylinders arranged horizontally in opposed pairs, like a Volkswagen Beetle or a Porsche 911. No production motorcycle had used this configuration before. Honda did not adapt a car engine. They designed a flat-4 from scratch specifically for this motorcycle. The engineering reasons were sound and the advantages were real. A flat engine has an inherently low center of gravity because the cylinders sit below the crankshaft level. The opposing pistons cancel each other's vibrations naturally, producing smoothness without balance shafts, and the wide, flat layout distributes weight evenly across the chassis. But the overbuilt aspect was the specification to which Honda manufactured this engine. The crankshaft was forged rather than cast, significantly more expensive, but dramatically stronger. The transmission gears were wider than necessary for the power output, adding durability at the cost of additional weight. The water cooling system was sized for a motorcycle producing twice the heat output. Honda built a motorcycle engine that was engineered like a small aircraft power plant and put it in a road bike. The first generation Goldwing weighed over 260 kilograms, heavier than many riders expected. But the engine was so smooth, so refined, and so utterly unstressed that owners simply kept riding them without encountering the mechanical limits Honda had built in. The Goldwing platform is still in production today, 50 years later. The fundamental concept has not changed, because the fundamental concept was right from the beginning. Honda just overbuilt the first version so thoroughly that refining it was easier than replacing it. We covered the engineering philosophy behind these indestructible machines in our last video, why old motorcycles killed so many riders and what manufacturers eventually did about it. If you want the full safety story, link is on screen now. Honda overbuilt with a new engine concept. Number 6, overbuilt in a way that is almost invisible because the motorcycle looks completely ordinary until you try to kill it. Number 6, Yamaha FJR 1300 2001. The Yamaha FJR 1300 does not look overbuilt. It looks like a sensible sport tourer for a sensible person who wants to cover long distances at reasonable speeds. Nothing about its appearance suggests that it was engineered to a standard that most manufacturers reserve for their flagship racing machines. Look closer. The engine is a 1298cc inline-4 with forged pistons, a forged crankshaft, and fracture-split connecting rods, a manufacturing process typically reserved for high-performance racing engines because of the cost. Yamaha used it on a touring motorcycle. The shaft drive uses a double cardan joint system that eliminates the reaction torque other shaft drive bikes produce when accelerating. The frame is aluminum and was designed using finite element analysis to a safety factor that significantly exceeds the loads any civilian rider would produce. Police forces across Europe, Australia, and the United States adopted the FJR 1300 precisely because of this hidden engineering margin. Motorcycle officers ride harder, longer, and more aggressively than any civilian. They need a machine that does not degrade under sustained abuse. The FJR 1300 gave them that and then some. Civilian owners who buy an FJR 1300 and ride it gently for weekend touring are using roughly 20% of the motorcycle's engineering capacity. The remaining 80% sits there silently, waiting for demands that most riders will never make. That is what overbuilt means when it is done properly. The excess capacity is invisible until you need it, and you almost never need it. The FJR 1300 hid its engineering. Number 5 did the opposite. It announced its engineering so loudly that Honda only sold it in limited numbers because each one was too expensive to build. Number 5. Honda VFR 750 RRC30 1987. Honda built the RC30 for one reason: to win the World Superbike Championship. Homologation rules required a minimum number of road-legal units to be sold before a machine could race. Honda needed a street bike. What they actually built was a factory race bike with mirrors and indicators. Each RC30 engine was hand-assembled by a dedicated team at Honda's Hamamatsu facility, not on a production line, by hand. Individual technicians were responsible for individual engines. Titanium connecting rods, a material so expensive that most manufacturers would not use it even in dedicated race bikes. Gear-driven camshafts instead of timing chains, because gears are more precise and do not stretch over time. a close ratio gearbox designed for circuit use. The chassis was equally excessive, a single-sided swing arm, the first on a Japanese production motorcycle that allowed rear-wheel changes in seconds during pit stops. Magnesium engine covers to save weight, a fuel tank shaped by wind tunnel testing. Honda priced the RC30 at roughly 3 times the cost of their standard VFR 750. Even at that price, they reportedly lost money on every unit because the hand assembly process and premium materials could not be recouped at the volumes homologation required. The RC30 won the inaugural World Superbike Championship in 1988. It won it again in 1989. Fred Merkel rode it to both titles. The motorcycle did exactly what it was built to do, and it did it because Honda refused to compromise on a single component. Today, clean RC30s trade hands for 6-figure sums, not because they are rare, although they are, because they represent an era when a manufacturer built the absolute best motorcycle they could build, regardless of whether the price made any financial sense. Honda built a race bike for the road. Number 4, built something more quietly remarkable, a sport tourer that simply refused to stop running. And the numbers its owners have documented are almost impossible to believe. Number 4, Kawasaki Concours GTR 1000. 1986. The Kawasaki Concours does not appear on most lists of overbuilt motorcycles. It is not exotic. It is not hand-built. It does not use aerospace materials or radical engineering concepts. It uses a modified version of the GPZ 1000 RX engine, a steel frame, and a shaft drive system. What makes it overbuilt is what happens after you buy it. Concours owners have documented engine mileage figures that belong in a truck forum, not a motorcycle forum. 200,000 miles is common enough to generate casual discussion rather than surprise. 300,000 miles has been documented with photographic evidence. One owner on the Concours Owners Group forum reportedly crossed 400,000 miles on the original engine before a rod bearing finally required attention. 400,000 miles on a motorcycle engine. For context, that is the equivalent of riding around the Earth at the equator 16 times on one engine. The reason comes down to engineering margins that Kawasaki never advertised. The engine internals were specified for significantly higher loads than a touring motorcycle would ever produce. The shaft drive was overbuilt to handle sustained high-speed cruising with a loaded bike and passenger for hours at a time. The cooling system was sized for worst-case scenarios that most riders would never encounter. If you asked Kawasaki in 1986 how long the Concours engine was designed to last, they would probably have said 100,000 miles. The fact that owners routinely quadrupled that figure tells you how conservative the engineering margins actually were. The Concours overbuilt in silence. Number 3, overbuilt in the loudest possible way. Because the man who designed it believed that a motorcycle should be a work of art first and a machine second, and he was willing to bankrupt the company to prove it. Number 3, MV Agusta F4, 1998. Massimo Tamburini designed the Ducati 916, widely considered the most beautiful motorcycle ever made. When he moved to MV Agusta, the motorcycle world expected something exceptional. What they got was something unreasonable. The F4 Serie Oro, the first version, limited to 300 units, used a radial valve inline-4 engine with titanium connecting rods, magnesium engine covers, carbon fiber bodywork, and a single-sided swing arm with a CNC-machined aluminum frame. Every visible component was finished to a standard that most manufacturers reserve for show bikes, not production machines. Tamburini famously insisted on redesigning components that were already approved for production because they did not meet his visual standards. The exhaust system was revised multiple times because the pipe routing did not look correct from specific viewing angles. The frame was polished to a finish that served no engineering purpose but satisfied Tamburini's conviction that the structure of the motorcycle should be as beautiful as its surface. The cost of this perfectionism was real. MV Agusta reportedly lost money on every Serie Oro unit. The standard F4 that followed was more commercially viable, but still manufactured to tolerances that made the accountants uncomfortable. Tamburini did not care. He was building a monument, not a product. The F4 remained in production for over 20 years, one of the longest production runs of any Italian superbike. Tamburini's overbuilt vision outlasted every cost-cutting argument that was made against it. If you care about the engineering decisions behind the machines, not just the horsepower numbers, subscribe. We go deep on this stuff every week. And what is coming at number 1 takes overbuilt into territory that genuinely has no comparison in motorcycle history. Tamburini overbuilt with obsession. Number 2, overbuilt with something even more extreme, money. So much money that Honda created the most expensive production motorcycle in history, and then lost money on every single one. Number 2. Honda NR750, 1992. Honda spent 8 years and an estimated $100 million developing a motorcycle engine with oval pistons, not round, oval. The concept is difficult to grasp until you understand the problem Honda was trying to solve. Racing regulations limited engines to 4 cylinders. Honda wanted the performance of an 8-cylinder engine. Their solution was to make each of the 4 cylinders oval-shaped, with 2 connecting rods per piston, essentially creating an 8-cylinder engine that technically only had 4 cylinders. Each oval piston had 8 valves, 32 valves total in a 4-cylinder engine. The engineering required to make oval pistons seal properly, reciprocate smoothly, and survive racing loads was so extreme that Honda's own engineers described the project as operating at the boundary of what was mechanically possible. The road-going NR750 was priced at $50,000 in 1992. Adjusted for inflation, that is roughly $110,000 today. It was the most expensive production motorcycle ever sold at the time. Honda made approximately 200 units. Every component was manufactured to a standard that made the RC30 look mass-produced. Carbon fiber bodywork, titanium connecting rods, magnesium wheels. The fuel tank was made from carbon fiber and titanium. The instrument cluster was fully electronic, with an LCD display. In 1992, when most motorcycles still used analog gauges and cable-driven speedometers, the NR750 never won a race. The oval piston concept never achieved the racing dominance Honda had envisioned when they started the project in 1979. In pure competition terms, the 8-year, $100 million program was a failure. But the technologies developed for the NR program, electronic fuel injection systems, advanced metallurgy, computerized engine management, filtered into every Honda motorcycle that followed. The CBR 900RR Fireblade, the RC211V MotoGP bike, the current CBR 1000RRR. All of them carry DNA from the oval piston project that never won a championship but advanced Honda's engineering capability by a generation. Sometimes the most overbuilt machines are not the ones that succeed. They are the ones that teach the manufacturer how to build everything that comes after. Honda overbuilt with money. Number 1, overbuilt was something no motorcycle manufacturer had ever used before. Because the company that built it does not just make motorcycles, they make jet engines. And they use that knowledge to build a machine that operates outside the frame of reference of professional racers who have spent their entire lives going fast. Number 1, Kawasaki Ninja H2, 2015. Kawasaki is not just a motorcycle company. They build ships, they build railway rolling stock, they build industrial robots, and they build gas turbine engines for power plants and aerospace applications. The Ninja H2 exists because someone at Kawasaki Heavy Industries asked a question that no motorcycle manufacturer had asked before. What happens if we use our aerospace division to design a motorcycle component? The answer was a centrifugal supercharger. Not a turbocharger. Those are driven by exhaust gases and have lag. A supercharger, mechanically driven directly from the crankshaft, delivering instant boost with zero delay. Kawasaki's supercharger was designed by their gas turbine and machinery company using computational fluid dynamics tools developed for jet engine compressor blades. The impeller spins at up to 130,000 revolutions per minute. For scale, a typical turbocharger in a performance car operates at around 80,000 to 100,000 revolutions per minute. The Kawasaki supercharger exceeds that by 30% because the engineering tolerances, borrowed directly from aerospace manufacturing, allow the impeller to operate in a range that conventional automotive components cannot safely reach. The street-legal H2 produces 228 horsepower. The track-only H2R produces 321 horsepower. A journalist at motorcycle.com took a stock H2R from a standstill to 200 miles per hour in 13.9 seconds. World Supersport champion Kenan Sofuoglu reached a verified 248 miles per hour on the Osman Gazi Bridge in Turkey on a stock machine. Professional racers who have ridden the H2R describe the acceleration not with comparison to other motorcycles, but with comparison to the absence of comparison. They say it exists outside their existing frame of reference. These are people who race for a living, who have spent decades going fast on the fastest machines available, and they say the H2R is beyond what they already know. That is not a marketing claim. It is testimony from professionals who have no reason to exaggerate. The paint on the H2 uses a self-healing clear coat. the first application of this technology on any mass-produced vehicle, car or motorcycle. The mirror finish was designed to resist swirl marks and minor scratches by chemically rebonding at a molecular level after surface damage. Kawasaki named the H2 after the 1972 H2 Mach 4, the Widowmaker, from the introduction of this video's predecessor. That naming was deliberate. The original H2 was overbuilt on power and underbuilt on everything else. The modern H2 is overbuilt on everything: the supercharger, the frame, the aerodynamics, the paint, the electronics. Every single system was engineered beyond what was necessary because Kawasaki had access to engineering disciplines that no other motorcycle manufacturer possesses. That is why the Kawasaki H2 sits at number 1. Not because it is the fastest, not because it is the most expensive, because it is the only production motorcycle in history where the critical performance component was designed by engineers who normally build parts for jet engines. That is what Overbuilt looks like when a company with aerospace capabilities decides to build a motorcycle. Everybody else is borrowing technology from the car industry. Kawasaki is borrowing it from the sky. Which one surprised you most? And which Overbuilt motorcycle did we miss? Drop it in the comments. Best suggestion gets a dedicated video. Now, if you want to know the other side of this story, what happened when manufacturers did the opposite of overbuilding, when they cut corners and riders paid the price, we covered that in detail. That video is on screen right now.